Hey everybody, in this video we are going to learn how to solve a system of equations using matrices, in particular using Gaussian elimination and Gauss-Jordan elimination. So first we need to introduce a couple more terms for some different types of matrices. First one is a diagonal matrix. So a diagonal matrix is a square matrix whose only non-zero entries are on the main diagonal. So here you can see I've got zeros everywhere except for the numbers along the main diagonal of this 3x3 matrix. So just a note, if you were to multiply two diagonal matrices, you would get another diagonal matrix. So just kind of a nice thing that we'll run into in later sections. The other definition I want to mention is upper triangular form, because this is going to come up later. So this just means that the bottom, if you were to look at everything below the main diagonal, you get all zeros. Above the main diagonal, you might have some zeros, but in that bottom left corner of the matrix, you're going to get all zeros there. Okay, so to talk about Gaussian elimination, we first have to talk about elementary row operations. So there are three elementary row operations that you can perform on a matrix. And if you do these, you get an equivalent matrix, right? They're not going to be looking exactly the same after you do an elementary row operation, but they will be equivalent to each other. The first operation I can do is I can switch two rows. I can just swap, say, row 1 and row 3 if I wanted to in a matrix, just switch positions of them. The second thing I can do is I can multiply a row by a non-zero number. So let's say I had a matrix where I had a row and I wanted to double every entry of just that row. I can do that. Or I can, multiply it by a fraction like 1/2 and cut all the values in half if I wanted to. And the third operation is we can replace a row by any multiple of another row added to it. So I could take, say, row 1 and row 2, and I could add them together. Or I could take and then replace either one of those rows with the new values. Or I could take row 1, multiply it by 2, and then add it to row 2 if I wanted to. Okay, very similar to what we did when we solved systems of equations. When we use the addition method, we might multiply one or both equations by a value and then add them. And so I can do the same thing with rows in a matrix. Two matrices are row equivalent if one can be obtained from the other by performing a finite sequence of elementary row operations. So I can do a whole bunch of these to a matrix and make it look very different. It would still be equivalent to the original matrix as long as I'm sticking to these elementary row operations. Okay, so now we're going to talk about echelon matrices. First one is a row echelon form that we can put an equation or a matrix into. And we're using the elementary row operations to do this. A matrix is going to be in row echelon form, sometimes abbreviated as REF. If all the leading ones or pivots are present. So in each row that doesn't have all zeros, because you can have a matrix with all zeros in it, but any rows that with some non-zero values in it, the first entry is a 1. So if I'm reading the row from left to right, the first non-zero value is going to be a 1. Okay? The next thing is if there are any zero rows, they're at the bottom of the matrix. And then the third one, we can call this a left to right staircase pattern. But this is where if I go from the top left down each row, the leading one in any row appears to the right of the one above it. So if I have a 1 in position in row 1, column 1, then the next row would be, at least 1 to the right, if not more, have its first non-zero. And it would just kind of go down from there. And we'll see this as we work through an example. All right, so those are the three things that you need for row echelon form. We're going to add for a technicality on 5 to get to a reduced row echelon form. So with this one, I have those first 3 still. So I need the leading pivots. My 0 rows need to be at the bottom, and I need to have this left to right staircase pattern going on with my leading ones. And then in addition to that, now I have to have zeros above the leading ones as well. So if I go down a column where a leading 1 is, I shouldn't have any other non-zero values in that column. So above and below that leading one should be all zeros in a reduced row echelon matrix. And we also have this idea of the reduced row echelon of a matrix is unique. This isn't something we can really check, but it is a property of a reduced row echelon matrix, which we'll kind of revisit at the end of this video. Okay, so let's just make sure we got this down by looking at a few examples. So here I have 4 matrices, all with a bunch of zeros in them. We want to see, are they in row echelon form, or are they in reduced row echelon form, or maybe neither? Okay, so just a reminder, for the row echelon form, we'll start there. We need the leading ones. We need the row order to be correct, where the 0 rows are at the bottom. And we need that left to right staircase. So looking at the first matrix here, I've got numbers all in the first column, or row, a 0 and then a leading 1 in the next column. So the staircase pattern is looking good there. And then the next 2 rows are all zeros until you get to that last column where I have 1. So I definitely have leading ones in every row. There's no non-zero rows, so there's no issue with row order. And I do have the staircase pattern. It's okay that my third row doesn't have a 1 in the third column, that it kind of skips over. As long as it's to the right of the row above, then that is going to be row echelon form. So that's an example of a matrix in row echelon form. If I start looking through these to see if the rest have this pattern, well, B does not have this pattern because it doesn't have leading ones in each row. There's a 5 as a leading value in the second row and a 7 as a leading value in the third row. So that one is not row echelon form, which means it's also not going to be reduced row echelon form because those have to all meet these first 3 requirements. For the third one, this one looks really great. It has 1s in the leading. It has a staircase pattern, and there's no 0 rows for a row order error. So that one is also row echelon form. The last one, well, the problem with this one is I have a row of all zeros in the middle of the matrix. So it is not in row echelon form because my 0 rows are not at the bottom. So A and C are the only 2 that are in row echelon form. Now let's look at reduced row echelon form. So I'm going to add that 4th requirement that above my leading ones, I have to have all zeros as well as below. So if I go back to the first one, well, this is definitely not the case. I can already see in the second row, my first leading one has a 5 above it. So that one's not in reduced row echelon form. B was not row echelon form, so it's also not reduced row. So the only other one that might be in reduced row echelon form is C. And if I look at that one, in each column with a leading 1 above and below, there's all zeros. So this one is also reduced row echelon form. And it's the only one of the 4 that is. And the other 2, well, they're not in either form. Okay, so hopefully you got a better idea of what it looks like in practice to have a matrix in one of these forms. Now let's get to how I use those to solve a system of equations. Okay, so looking at linear systems in this section, we want to take and be able to write these using matrices, and that's where the whole echelon matrix things come in. So let's say I have this very generic system of equations. Everything's generalized here using A's for my coefficients, x1, x2, and so on for the variable, and then my value on the right of each one of these equations we're using B for. So there's a couple of different ways that I can rewrite this. We're going to focus on one of them today, but first one is the matrix representation. I can take all the coefficients on the left side of each of these equations and make a matrix out of that. That would be the coefficient matrix. I can make a column vector matrix out of the x values and the b values as well, the constants on the right side of each equation. And I could write this as the matrix A times the matrix X equals the matrix B. So this is a nice matrix representation of the system of equations. And we'll look at this more in later sections, but for now we want to look at a different way of doing this, and this is an augmented matrix. So here I've removed all the variables. It's all just coefficients on the left and right side of the equation, and they're all fitting into one matrix. And we usually put a bar, either solid, sometimes you'll see a dotted line that separates the coefficients from the rest of the matrix. And they're there because they're affected by elementary row operations, but really we're focusing on everything to the left of the bar, all the coefficients, when we're talking about row echelon form or reduced row echelon form. So those are kind of along for the ride. They get affected by anything that we do to the matrix, but we're focusing on everything to the left. Okay, so let's see how we can use this in Gauss-Jordan or Gaussian elimination first. One other thing is, let's say I put an augmented matrix like this in row echelon form. Then if I have variables that correspond to the leading ones, because they will correspond, then because, say column 1, those are all the coefficients for x1. Column 2 is all the coefficients for x2, and so on. And so anything that's associated with the leading one, we call that a leading variable. And any variables that don't correspond to any leading ones, which can happen, we call those free variables. And so we'll see in an example how to deal with those free variables. Okay, Gaussian elimination. So this is a way to solve a linear system of equations by transforming its augmented matrix into row echelon form. And we're going to use our row operations to do that. And then once we get into row echelon form, we use back substitution to solve it. And we'll see in an example what exactly I mean by that. But our basic strategy is step 1, take your augmented matrix and put it into row echelon form. And a good way of going about doing this is you first identify the leftmost non-zero column. Make sure that one's right up top and you get a 1 in that first entry. So row 1, column 1, you want that to be a 1 if you can make that happen. And then you use row operations to get all the entries underneath that 1 to 0. And then you move to the next row or next column and you do the same thing. So get a leading 1 if you can, and zeros underneath it, and so forth, until you get to that upper triangular form where I have a diagonal and everything below the diagonal is 0. And then once we get into that row echelon form, we're going to use back substitution. So we'll revert back to variables and equations away from the matrix and then solve from there. And so just some notes here. If you get an augmented matrix that has all zeros in one of its rows, if it's all zeros all the way across, then that equation is going to have infinitely many solutions. And if a row of zeros equals a non-zero number, so like everything to the left of the bar in the augmented matrix is 0, but on the right side I get a non-zero value, then that means there's no solution. Okay, so let's do an example where we can bring all this together. So we're going to do Gaussian elimination on this system of equations. We've got 3x1 plus 9x2 plus 12x3 equals 3. And then negative x4 minus x5 equals negative 5. And x2 plus 2x4 minus 4x5 equals 0. Okay, so first thing we got to do is convert the augmented matrix to row echelon form. So I'm going to pull out all the coefficients. Okay, and remember column 1 is for x1, column 2 is for x2, and so on until we get to the end. And then we have to put a bar and then our coefficients from the right side of each equation goes there. So I get a matrix that looks like this. So first row is 3, 9, 12, 0, 0, 3. Second row is 3 zeros and then negative 1, negative 5. And the third row is 0, 1, 0, 2, negative 4, 0. Okay, so hopefully you can see where I pulled all of that out to get that augmented matrix. And now I want to get this in row echelon form. So first thing is we usually try and get a 1 in that first position, row 1, column 1. Right now I have a 3. So if I multiplied the first row by 1/3, then that would give me a 1 in that first position. And we are going to leave ourselves instructions to what we did here. So you want to get this notation down. You might find other notations on the internet, but we should really be sticking to the same notation so that we can all have the same conversation about all this. So please refrain from introducing different notations you might see out on the internet. You want to adopt the notation we're using in this class. So I'm going to write it here right next to row 1. I'm going to do 1/3 times row 1. And the fact that I put it next to row 1 indicates that that's the row I'm changing. If you look at the notes that go with this video, then you can see an alternative where maybe it's not next to the matrix, where you can write it as well. Okay, so I'm going to take and rewrite my matrix, but now the first row is all multiplied by 1/3. So that becomes 1, 3, 4, 0, 0, 1 in that first row. So notice that my numbers to the right of the bar changed as well. Okay, so I've accomplished the first thing is I've got a 1 in row 1, column 1. The next thing I want is to start working towards that staircase effect, okay? And so I notice that my third row has a leading 1 before the second row does. So I'm going to swap those rows. So I'm just going to use to indicate this an R2 and R3 with an arrow going in both directions, just indicating that I'm going to just swap those two rows out. Okay, so now row 3 is now row 2, and row 2 is now row 3, and I will use those new names for them, so you don't have to keep track of their original names. Okay, things are looking pretty good. I've got leading 1s in the first 2 rows, and they're in that staircase pattern. If I look at the third row, I don't have a leading 1 yet, so that's what I want to work on next. And if I just took and multiplied that -1 by a negative, then I'll get a positive leading 1 in that position. So that's what I'm going to do. And oh, my notation didn't come with me there. There it goes. Okay, so I'm doing -1 times row 3 just to change that leading 1 to a positive. And now I get my matrix, and it's in reduced echelon form. It meets all the requirements, those 3 requirements for reduced echelon form, which means I've completed the first step of this process. And though I picked a shorter one here that wasn't too bad, these can get rather lengthy. Okay, so just take your time with them and be careful not to make arithmetic mistakes that will drive you crazy. Okay, so the next step is going to be to convert this back to a system of equations and use back substitution to solve it. So I'm going to rewrite this now, remembering that column 1 is my x1, column 2 is x2, and so on, and write all these coefficients back into my equation. And this is what I get from my new equivalent system to what I started with. Now, something to point out is we do have a lot of zeros in here, and it does turn out we have 2 free variables. So if you notice in column 3, there is no leading 1, so that's a free variable. And column 4 also doesn't have a leading 1 because the leading 1 was in column 5 doesn't have a leading 1 because column 4 is where the leading 1 was for that last row. So that means I've got 2 free variables, x3 and x5, because those are the columns where there's no leading 1. So we're going to see how we have to deal with that now. Okay, for back substitution, here's our system that we came up with from our reduced row echelon form, row echelon form of the matrix. And we identified that we had 2 free variables. So I'm just going to give those new names to make it a little bit easier to work with these. So I'm going to say x3 is S and x5 is T. And now I'm going to back solve here. I'm going to go plug those into the equations and see if I can get an expression for all 5 variables by the end of this. So I'm going to start with the bottom equation. It only has 2 variables in it, and one of them is my free variable. So I'm going to start there. And I'm going to replace x5 with t, and then solve for my unknown x value, x4. So subtracting the t over x4 is going to equal 5 minus t. Okay, so now I have definitions for x3, x5, and x4. I just need one for the rest of the variables. So I'm going to go to the second equation now. I'm just working my way up the system. And that one has x2 and then x4 and x5, which I have definitions for. So I'm going to substitute all that into that second equation. So x2 plus 2 times x4 becomes 2 times 5 minus t, minus 4 times t, replacing the x5 there, all equals 0. I'm going to clean this up a little bit and solve it for x2, and I'll have a definition for this variable as well. So distributing the 2, I'm going to get 10 minus 2t minus 4t, and then we'll combine the like terms there. So x2 plus 10 minus 6t equals 0. And then move everything that's not my x2 over to the right side of the equation. So x2 equals 6t minus 10. So I've got 4 variables down, 1 to go. Just need a definition for x1 and I'll have my solution. So going to that first equation, x1 plus 3x2 plus 4x3 equals 1. I'll substitute in what I have for x2 and x3. So I end up with x1 plus 3 times 6t minus 10 plus 4s equals 1. And just like with the last one, I will simplify this and move everything that's not x1 to the right side of the equation. So distribute the 3 to 6t minus 10. And I don't have any like terms here, so I'm just going to move everything over to the other side. So I get x1 equals negative 18 minus 4s plus 31, because I added the 30 over and combined it with the 1 that was already on the right side. All right, so it's kind of all over the place. So I'm going to summarize it, but I do have a definition for all 5 variables in terms of s and t. And if I had values for these parameters, s and t, then I could get a solution for the whole system. Okay, so that's what it looks like when you end up with free variables. Is you're still going to have some variables, but you should get a definition that minimizes the number of variables for all of your unknowns there. Okay, so that's how you do Gaussian elimination. Gauss-Jordan elimination takes everything a step further. And instead of stopping at row echelon form, you continue to reduced row echelon form. This one means that you're going to have to spend more time working with the matrices, but it does not require that you do any back substitution. If you get it all the way down to reduced row echelon form, you will be able to look at the matrix and see, okay, x1 equals this, x2 equals that, and so forth, without having to do all that back substitution that we just had to do. So it's definitely a nice advantage to this method. So step 1 is to take that augmented matrix, convert it to row echelon form, and then you keep going. You get it once you get in row echelon form, and now you make sure that above all of your pivots, all above the leading ones, you have zeros as well, and you don't stop until that happens. So you get it into reduced row echelon form. Okay, so we're not going to do an example of that in this video, but we just take what we started in that last example and take it a few steps further. Some last notes about echelon forms of matrices and their equivalence and uniqueness that is helpful to know. Every non-zero matrix is row equivalent to a matrix in row echelon form. So that means that you can take any matrix and get it into row echelon form. So that you're never going to run into a situation where you have a matrix that can't be put into row echelon form. So if you run into some hiccups while trying to do it, don't give up. It is possible, no matter the matrix you're dealing with. The second thing is that every matrix is equivalent to a unique matrix in reduced row echelon form. So this is important, that word unique, because it means that no matter what you do or what order you use your elementary row operations in, maybe you have a study partner and you guys make different choices about what the order you do things in or the way that you reduce it. When you get to that reduced row echelon form, you should end up with the same matrix no matter what. So that uniqueness is kind of nice. It's only true with the reduced row echelon form here. Your row echelon forms might look different, but when you get to the reduced row echelon form, you should have the same matrix at the end. Okay, I hope you're ready to get started with some Gauss-Jordan elimination and Gaussian elimination now.